the people has taken the initiative to have the advancement or automations in those areas. So in advancement manufacturing process specialization in the designing and development of the equipments, machinery to optimize manufacturing operations, this technology is transferring the manufacturing industries as it can reduce the design to production time, reduce the production costs. The technology reduce the wastage, ensured greater flexibilities in the productions. The technology involved in the advanced manufacturing can be divided into three main groups, that is efficient production, intelligent productions, and effective organizations. Some of relevant production technologies includes rapid prototyping, near net shape manufacturing, precision castings, machining, joining techniques. However, today manufacturing industries focus on intelligent productions, that is use of artificial intelligence, the Internet of Things, 3D printing, virtual realities are just a few new manufacturing technology, but they are steadily becoming more common in manufacturing practices. You all might be aware that nowadays people are focusing on the IoT, the artificial intelligence, and so on. So technical institutions always believe that engineering students are the future and that will help in making our country great. And we faculty members used to encourage their ideas. We conduct many seminars, NIT Agartala or IITs or RTC CITs or many other organizations across the country or the globe. They are organizing seminars, workshops, STPV for faculty development programs, conferences to extend the knowledge and update ourselves towards the recent development in the area of manufacturing. So I am sure this faculty development program will help to participate to achieve the knowledge and inculcate themselves and will help in contributing to the betterment of the societies and in large graduating engineering professionals or your students. We know that every individual is talented in their way. Everyone have their area of interest, hobbies, and passions, scoring well in academic and being a topper in one thing. But the inner talent that everyone has it another. One should identify their own passions and work accordingly and excel themselves towards their area of interest. And as Arvind is one of my students who has completed PhD from NIT Agartala, his area of interest is in the composite materials and manufacturing, and further he wants to excel himself in the area of automations. So definitely, as I have seen the brochures, we observe the many experts like Dr. Krishnaiah, Dr. Vidyut, and some of the scientists who is coming from the different organizations, have their expertise in those areas and will deliver it. It will be helpful for the coordinators, co-coordinators, other faculty members, and the participants. So with these words, once again, I thank organizer for giving me an opportunity to deliver a one talk on the aluminum composite materials, aluminum-based composite materials. So I wish that this program of the 5 days will have the grand success. And with these words, I conclude my wishes for this program. And now I will start my talk on the topics aluminum-based metal matrix composites. I think I am audible to everyone. Hello.
Yes, sir.
So thank you all, and particularly the principal sir, who has given the opportunity to Arvind to organize a 5 days faculty development programs, and their friends, Dr. Jay Prakash. So I wish they will excel their performance in the college, and definitely they will be the assets of the institutes. So I wish for grand success of this program. Thank you.
Thank you, sir. Thank you, sir. Thank you very much, sir. Now, sir, you start your session, sir.
Session, na? Okay.
Yes, sir. Yeah, please share your PPT, sir.
PPT is visible? No, no.
No, sir. Now it's visible, sir.
Visible. So, dear participants, today I have been given one topic to deliver the few informations about the aluminum alloy-based metal matrix composites. So, before starting of these topics, we should discuss about the background of these composite materials. You all are aware the composite materials is also slightly different than the alloy, and here two or more than two individual elements combine together and form a new materials, and then those materials have the better mechanical properties than the individual elements, and this is nothing but called as a composites. And why we people are interested for the composites? It may be aluminum, it may be metal, it may be a fiber, it may be a polymer, or it may be a different matrix, glass fiber, or different, and so on. So it will give the better properties. See, nowadays, or you might be aware that Hero Honda cars or the different automobile vehicles, their engines, or you can very well remember everyone that the earlier motorcycle engines, if you remember the Rajdoot and other motorcycles, their engines are very means whole body structures as well as the engines are having the high weights or heavy weights, and the materials which are nowadays it is replaced by alloy, aluminum silicon alloys, and the car engines are also coming as a aluminum silicon alloys or many aluminum copper alloys, or it's have the better different applications in the area of automobiles or the aircraft and all. So nowadays further alloy is also is replaced by a composite material because of its lightweight. So it's have the lightweight and have the better mechanical properties compared to the alloy or the individual steels, or if you compare with the other alloys. And if the strength is better, other mechanical properties is better, then what is harm to use of it? So we can we can have the certain properties, and because of that we are using the composite material. So why composite used in the engineering? Full screen is visible, Arvind?
Yes, sir. Now it is visible, sir.
So it is a weight saving, then corrosion resistance, it have the properties, fatigue properties, manufacturing advantages, the reduced parts count, novel geometries and low cost toolings, design freedoms, continuous properties spectrums. Arvind, just a minute. हेलो, हाँ वो मैं बाद में कर लूँगा, अभी मैं एक लेक्चर दे रहा हूँ. So this composite materials, that is the fundamental consideration is how do composites materials differ from the other engineering materials? What are the constituent materials and how do their properties compare? And how do the properties of the composites depends on the types, amounts, arrangements of the constituents, and how are composite products made and why does manufacturing aspects qualities. So means we have to compare, and if after comparing, if we feel that it's have the better properties, we can go for the replacement of it. And but it is not having the widely use. Why it is not having the widely use? We have a plan, or the scientists having the planning to replace those alloys by the composite materials. Yes, they have success also, but not the many components or many applications. The reason is it's having the this is costly, the lack of design standards, and some of the productions or manufacturing constants, and also so play a important role into it. So if you see the composites, in that there are two constituents. One is the matrix, another is the reinforcement. The matrix may be any kinds, so we'll see one by one, but this is the about the some of the applications where we can have the composite materials applications, or this either this is called as a sorry, this is metal matrix composites. So there we can use these are the applications. Now that in constructions also it is used. If we talk about the advantages, it's have the authentic appeal, ability to mold complex shapes, barrier surface finish, and lightweight, durability, and corrosion resistance. So these are the advantages of this. So huge potential for the polymer composites in the civil engineering. But our topic is to go into the metal matrix composite, that is aluminum based. So just I am showing the some of the this photographs to understand these fibers and all. This is the carbon fibers, and nowadays these composite materials are called as a novel materials. The materials which is used in the present era for the constructions, engineering, and scientific purpose are called the novel materials. And if you remember the born in the stone age, then stone, wood. So slowly development has taken place. Then wood, polymers, ceramics, and other applications. So materials have the control role in all fields of engineering. The reuse and recycling components of the novel materials is often very poorly throughout. However, appeal is to the environmentally conscious. For example, product that can be recycled or biodegraded. So in the present era, the rechargeable lithium batteries, you all are aware that the cars or automobiles which are coming as a electric. Hello. हाँ. Good morning. Oh, सूरज को भेज दो मेरे क्वार्टर में साइन के लिए. हाँ. So this I was talking about the lithium batteries. So the car which is coming out, this is rechargeable batteries are there. So electric car, it is very popular. Fuel consumptions will be very less, or it is a lot less costly and all. So those are this is biodegradable or not. So people are working on it and how long it will give the discharge means charging and all. So those are the areas people are focusing. So further we can say that smart materials or the composite materials or nanoparticles materials comes under the novel materials. So this may be the composite materials, and our aim is to focus on the metal matrix composite and the processing of the metal matrix composites and so on. So we have already discussed these composites are the combination of the two materials in which one is the materials is called the reinforced phase and in the forms of fiber, or it may be particles, or it may be embedded in the others material called as a into the matrix. So if you see the function of matrix and the function of the reinforcement, we will find this is the binds the fiber together. So the matrix, if we'll see this RCC structures also in the civil constructions, you will see the cements and sand and water have the mixtures, and the rod is the reinforcement. It's working. It is working as a fiber, but those cements and others are holding those fibers. So similarly, in the metal matrix also, we have a fibers, matrix. It may be aluminum based, it may be a magnesium based, or it may be a copper based. Depends on it should be a ductile in the natures. It should not be a hard or brittle in the natures. So those materials are chosen as a matrix material, and it's have the different functions. And then the other section is the reinforcement. Those reinforcement, it may be a particles, it may be a fiber and so on, and it's have the certain properties or certain functions. So if we talk about the functions of the each, that is matrix and the reinforcement. So the function of the matrix is binds the fiber, means it will hold the fibers and provides a rigidity and shape to the structures and isolates fibers to slow crack propagations, then surface qualities and corrosions and wear protections for the fibers. Because aluminum, if we talk, or the copper, if we talk, or magnesium, they are the corrosion resistance. Or so these are the providing certain properties or adding the properties into those. Matrix will supply the certain properties. Now fill out certain functions. If we come to the reinforcement, we have a 70 to 80% of the load carried by the fibers. So what is the function of the fibers or the reinforcement? It will carry the load, maybe 70 to 90% of the load with the, and if we talk about the fibers, fiber cannot carry the load. It will only holds the matrix. It will holds the reinforcement. Then provide the structural properties to the composites like stiffness, strength, thermal stabilities, and provide electrical conductivity or the insulations. So necessity of the composite materials. Composite offers significant weight saving over existing metals, and since coefficient of the thermal expansions is low compared to the conventional materials, composites are used in satellite or for the space applications. Fiber composites have the specific tensile strength about 4 to 6 times greater than that of the steels and the aluminum. And of course, corrosion resistance. So characteristics of the composite, that is low weight, high strength, high stiffness, high wear resistance, and high fatigue life, higher working temperatures. We'll talk about the disadvantage. Of course, it is a cost is one factor. Fabrication is also another factor having the cost effects. Then repair can be difficult in the case of composites. Wider range of the variabilities. Then operating temperature can be an issue for the polymer. If it is a polymer, we cannot go the more than 500 Fahrenheit or and so on. But if it is a metal matrix, then we can go for up to the 2700 Fahrenheit. So properties is a non-isotropic, makes the design difficult, and then inspections and the testing typically more complex. Now we'll see the classification of the composite according to the morphology of the reinforcement. If we talk about the reinforcement and its arrangement, we will see that it is a unidirectional fiber composite. So in this directions, the composite, the fibers are focused. So it's have the strength in unidirections. But if we talk about the second, this laminated composites, so mostly you have seen now they are replacing it. But on railway stations, or in maybe cinema hall, or in maybe different occasions or different places, you will find the chairs which is made of the laminated composites. Then the short fiber means fiber size is a small and a small. So this is, and then this is a particulate style. And if you see the alignment of those the particulates or the this, so alignment, this is continuous alignment, and then alignment, and this is the random one, or the, you can say that is continuous. Now the matrix have the certain properties, and fiber have the certain properties. And as I said in the definition itself, by combining the both individual materials, and it will give the certain strength, and which is having the engineering applications. So if you see this stress strain diagram, then you will see the blue colors. It is softer materials. So you will see the matrix. This is the properties, and thereafter you will find the it happening because of the ductility, but the reinforcement or the fibers is brittle in the nature. It's having the very less ductilities. So once you will apply the loads, its failure will take place over here. But if you combine both, if you form a individual and combine together and form a composite materials, it's have the combined properties. So here, this is the green color is showing the the properties of the composite material, because it's having that. So ductility has reduces, and that here it has the tensile. So means slightly ductility. It is a combination of not either more ductile, or not either it is a very hard or the brittle. It is in between, and moderate ductilities is there, and strength is also. So we can have the better properties. So we can understand from this graph. Classification of the composite according to the type of matrix. If the matrix is metal, we can say the metal matrix composite. If it is a polymer, we can say the polymer matrix composite. Elastomer, then we can say the elastomer matrix composite. If it is glasses, then glasses matrix composite. If it is a ceramic, is the matrix materials, we can say the ceramic matrix composites. So metal matrix will, and our aim is to focus over here on the metal matrix composites. So metal matrix, like aluminum may be the matrix, titanium may be the matrix, magnesium may be the matrix, iron may be the matrix, copper may be the matrix, nickel may be the matrix. Like examples are, say, aluminum silicon carbide. As I said that it's have the wide applications nowadays. Then this is aluminum oxides. Then aluminum is the base matrix, and then titanium TiC is the reinforced particles. Here aluminum oxide is the reinforced particles. Here silicon carbide is the reinforced particles. The B4C, I think Arvind has worked on this B4C. So if the boron carbide is added as a reinforced in the aluminum matrix, we can have the boron carbide. If it is the titanium carbide added into the magnesium as a matrix, that is so we can have the magnesium matrix composites. And copper alloy, this is the duralium. Aluminum and copper is together. If copper is 0.45 or 0.43 to 45 to 0.48, so this comes under the, we can call as a duralium. And this duralium having the wide applications. You all are aware this, the aeroplanes. In aeroplanes, materials are used as a duralium, and it's have the very wide applications. And the high strength, high stiffness, the abrasion resistance, dimensional stabilities, and high temperature resistance, and the toughness will develop in those composite metal matrix composite materials. So the metal matrix composites are the class of materials with the ability to blend the properties of the ceramics, that is high strength and high modulus, with those of the metals or the alloy, to produce the significant improvement in the mechanical performance of the composite over those of the monolithic metals or the alloys. Aluminum alloy based metal matrix composites reinforced by the hard ceramic particles have become the attractive for the automobiles, structural applications, and the addition of the ceramic particles such as titanium borides, titanium carbide, titanium nitrides, silicon carbides, and aluminum oxides to an aluminum based matrix does not considerably change the density of the materials, but instead it usually leads to the significant rise in the specific strength and the modulus of the composites. So as I said that those examples I have shown you, this is the silicon carbides, aluminum oxides, or titanium carbides. So these are the having the high temperature, means these materials can withstand the high temperatures and contribute the high strength, and not only that, it is having the very good wear resistance. So in the engine's ring, or the where the wear are minimum, or to avoid there, this can be having the applications. In the recent years, these are the aluminum, magnesium, aluminum, titanium, aluminum coppers, aluminum silicon based metal composites become the very popular. So if we talk about the advantages, these composites are mainly used to provide the advantage over the monolithic metals, and then over the polymer matrix composite also, and this includes the higher elastic properties like high service temperature, insensitivity to the moistures, high electric and thermal conductivities, and better wear resistance. So if you see this over here, this is the fiber tensile modulus, and the different aluminums, it may be alumina or the silicon carbide or aramide or borons, and the different materials. And if you see this, they are the tensile fiber tensile modulus, and in the case of the graphite, you will find it is more. And then if you see the fiber of different silicon carbide or the borons, and you will find accordingly the strengths are better. So now you all are aware about the matrix. Based on the matrix, have the different composites, and then you have the metal matrix composites. And in metal matrix composites, you have seen this aluminum, copper, magnesium, and so on. The matrix and the reinforced particles. It may be a titanium, it may be a silicon carbide, or it may be a aluminum oxides, or boron carbides. But processing is also one of the factors which will play an important role to have the or the great challenge to the industries, so that it should have the minimum cost and have the wide applications. So there are different processing techniques. With the help of that, we can have the processing of or the manufacturing of the aluminum based metal matrix composites. So the traditionally discontinuous reinforced metal matrix composites have been produced by the several processing routes such as powder metallurgy, spray depositions, mechanical alloyings, and various casting techniques such as squeeze casting, reho castings, and the compo castings. So one of the methods, the in-situ techniques he has used, the Arvind's, while he was doing his research work at NIT Agartala. So there are a different way or different techniques by which one can have the manufacturing of alloys. It is widely recognized that the properties of the metal material are controlled by the size and the volume of the reinforcement, as well as the nature of the physics of the reinforcement. As we have discussed, Arvind,
Yes, sir. Yes.
it is from my end or from your ends or some other ends?
Now it's clear, sir.
Okay. So others, if they can off the mic, I think noise may not come.
All the participants are requested to kindly off your mic, please.
So what will happens, as we have seen the stress strain diagram, in there we have seen the matrix have the ductile properties, and the reinforce having the brittleness properties, and in combinations we have the composite materials, or it's have the combination of the both. So if our volume fractions of the reinforcement particles, if we contributed more, and bonding will be strong, differently it will have the very good strength. But the increasing the volume of those reinforcement particles is a very tough. If we add these reinforcement particles, the bonding will becomes the weaker. So it is a great challenge for the manufacturers or the persons who is going for the development of these composite materials. You have to compromise with the addition of volume fractions. So hardly if you add up to the Arvind, I think he has gone up to the 15% of those reinforcement particles of the maximum amount. If you increase the 20%, 30%, definitely a strength will increase, but at the same time, materials will not, the particles will not having the proper bondings, and we won't get overall. You will find that strength is becoming the poor. So it is an optimum range or recommended range up to the 15% if reinforcement particles. If you add into the matrix, you can have the better strength of the composite materials. So it is widely recognized that the properties of the metal matrix composites are controlled by the size and volume fractions. Size and the volume fractions of the reinforcement as well as the nature of the matrix reinforced interfaces. One more challenge will come that see these are the two combinations. One is the reinforcement, another is the matrix. So when we will go for the productions of or the manufacturing of these, the interfaces means the reinforcement particles and the matrix both are the different in the natures. So if the bonding is not properties, then you won't have the good strength. So that interface will play important role and importance this at interface having the adhesions quality, or we can say that affections or attractions toward the others, the matrix or the materials, so that it can have the good. And if it is not, then you have to add the some of the the activating elements which can increase the bonding or the strength at the interfaces. प्रसाद देखो देखो कोई आया है तो हेलो हाँ वो फाइल दे दो लेके आ जाएगा पर घंटी बजा दो आ जाएगा कोई. The work on the Metal Matrix Composite has led to the development of the new classes of the composites called the Institute of Metal Matrix Composites, and in which the reinforcement are synthesized in a metallic matrix by chemical reactions between the elements or between the elements and the compound during the composite fabrications. A variety of the processing techniques have been involved over the last decades is an efforts to optimize the structures and properties of in situ ceramic phase reinforcement metal matrix composite. However, the terminologies in the literatures for the processing route is inconsistent and confused. So, Kokjak and the Prem Kumar have suggested that the in situ reactions can be categorized in terms of the starting phases such as gas liquid, liquid solid, solid liquid phases, but an effective categorizations and naming of the processing routes have not so far been established. So many of the researchers further they are working, however they are developing by the following the gas liquid, liquid solid or solid liquid way. But just a minute, audience please, have a 1 minute. And where we categorize the processing methods utilized to manufacture the in situ metal matrix composites according to the temperature of the metallic matrix and the reactants during the processing. So now you people may be aware that in situ, and there are another way that is ex-situ. So in situ means whenever the reaction is taking place inside the liquid metals. So if you have added this is a matrix like aluminium matrix, and in that either titanium carbide or aluminium oxides or the silicon carbides or boron carbide you have added into it, and from the outside, then it is called as a ex-situ metal matrix composite, But if I am adding as a, suppose if I need to develop a aluminum, titanium, carbide metal matrix composites. So in that aluminum, you have to take as a matrix materials and kept it in the furnace, and it will be melt. And then you have to add the titanium in the raw form, and titanium will react with the aluminum. It will form the titanium aluminide, or and at the same time the graphite powder you have to add, or the activated charcoal if you will add, and then all three will react and it will form the titanium carbide at the higher temperature, so it to avoid the aluminum carbide which is brittle in their nature. So you will get the proper properties or proper strength. So this kind of inside the melt, it will react with the titanium, will react with the carbon, it will form the titanium carbide. Aluminum will react with the titanium, it will form the titanium aluminides. So you will find that it is a combination of those two reinforcement particles. It will form those reinforcement particles develop inside the metals or inside the liquid metals, and hence it is called as a in situ metal matrix composites. So method for processing of the aluminum alloy based metal matrix composites. Accordingly, the processing routes can be classified into the four categories. One is the solid liquid reaction process, vapor liquid solid reaction process, solid solid reaction process, and liquid liquid reaction process. So solid liquid interaction means reaction process. In this process, reactants like elements or the compounds react in situ to form the reinforcement phases in the presence of the third liquid, which I have explained right now, metallic phases, and reactants react with the some components in the melt to form the in situ ceramic reinforcement particles. So that way you can develop the composite materials. Another way is solid liquid reactions. So solid liquid reaction means you have the liquid is the base matrix, and if you are adding the solid like B4C, this TIC or aluminum oxides, if you add, then it will form the reaction will take place between the solid and liquid and to form the solid liquid react. That is in other way you can say the Ex-situ. So according to the processing features, this process can be further divided into the small groups. Some of the frequently used processings are listed below, so like self-propagating high temperature synthesis, exothermic dispersions, reactive hot pressings, combustion assisted casts, direct reaction synthesis, the flux assist synthesis, and in our lab these facilities are available. So flux assisted synthesis are students are doing over here. Then rapid solidification processing. So we have that. हेलो, हाँ बोलिए। समय 1:15 में। ओके, थैंक यू। So self-propagating propagating high temperature synthesis developed by the scientists in the year of 1960 and refers to a process in which the materials with a sufficiently high heat of formations are synthesized in a combination way in the combustion wave, which after ignitions and so on. So these are the different way of the processings. Now we'll move to this schematic diagram is shown over here, how it has formed. That see, it is X, and if it is a Y, so ceramic phase is forming like elements X and Y, and then this is a matrix, and you will find the composite after heating or maybe mechanical alloying way or the some other techniques if you use, and then you will find this is the composite materials. So this is a summation of XY particles in the matrix. So the reactive hot processing techniques. So in these techniques also developed by the scientists, and the B2 TiB2 means titanium boride particles on the basis of XD techniques can be developed, and it encompasses both the exothermic conversions of reactants to in situ reinforcement and the subsequent hot compactions of the porous composite products. So you might have heard nowadays that this the metallic foam. So metallic foams are the one of the products which can be developed by these techniques. And then this is a combination of assisted castings. So this slides I will share you. Then direct reaction synthesis. In the direct reaction synthesis refers to a process in which reactants powders or the compacts of the reactants powders are directly added into the molten metals, and the ceramic reinforcing particles are formed in situ through the exothermic reactions between the reactants and the between reactant and the some components of the metals. So this is the one other processing way. Then flux assisted synthesis. So so this is the, here we can use the potassium tetrafluoride and this potassium hexafluoro titrate. So these are the halide salts are used to enhance the the interfaces reactions, and or you can say the interfaces bondings, to have the bonding between the titanium and the borons, and it will improve the properties. So after the reactions, stirring is stopped in order to remove the slag containing the halide and this slags at the top from the molten composites, and is cast into a mold. So the maximum amount of the in situ form TiB2 is determined by the the viscosity of the subsequent melt. So values of up to the 12% volume fractions have been reported by this. And pure aluminum and the aluminum 4% of the coppers, that is A356 composites reinforced with the in situ TiB2 particles were successfully fabricated, and it's have the wide applications. So the flux assisted the synthesis, here we can have these facilities are available in our lab, and of course our a scholar has used this the facilities. So here activated charcoal they have used, and this is the furnaces where the heating has been done. Aluminum alloy melted, then in the crucibles, and this is the heating coils. So these are the line diagram of the setups. So rapid solidification process, and then introduction to vapor liquid solid reactions. So the different process are there, so by which one can develop those these composite materials. So I'm not going to talk much about this. The mechanical alloying, so you all are being a mechanical engineer, you might be knowing the mechanical alloying methods, where the powders are taken from the different elements, and then by alloying by using this the ball milling machines and so on, we can have the mechanical alloying of a solid state powder processing methods. So in that case, the different powders of the individual elements will be taken, it will place into the machine, that is ball milling machines, where the mechanical alloying means it will be alloyed, and then later on it will be compressed, and then we will get the composite materials. So we can talk about this is a solid state powder processing methods, which involves repeated cold drawing and the fracture of the particles as a result of the high energy ball sample collisions. And this method can be used to produce fine grained alloyed powders particles in the metals and metal ceramic systems. So my dear participants, by these methods we cannot go for a mass productions or the bulk productions. For the small components where the high properties is required, that can be only used by this mechanical alloying process. The reason is, here we have the two individual particles, or it is in the solid states, and in the mechanical alloying there are different balls, and that ball will compress those the particles, and then what will happen is those particles will have the collides between each others, and the high energy ball sample collisions, and then later it will be impacted, and then you will get this. So if you cannot go for the mass productions in these cases, of course this having the much good properties. So this method can be used to produce the fine grained alloy powder particles in the metals, and the aluminum, sorry, this aluminum carbide particles are formed by a mechanical alloying of the aluminum with the carbons and subsequently annealing of the mixtures powders. And after annealing of the powders mixture at the temperature of 873 Kelvin, aluminum carbide particles will form, and the size will be the of the zero point 0.4 or 0.3 microns. The reactive hot pressing by hot compressions also, there are machines we will powder you will take and then you will compress it, then also you can get it the this composite materials. Isothermal, the heat treatment process where this aluminum will react with the carbon titanium carbide and forming the titanium aluminide and the aluminum carbide. And again at the this equation 1, and if you go at the higher, this is available in the lower temperature, but here at the higher temperature again this titanium aluminide will decompose and the titanium will separate out, and this titanium will react with the carbon and form the titanium carbides. Then liquid reaction process. So now if we'll talk about the applications. So application of the metal matrix composites, it have the space application, it have the military applications, it have the transportations. So the space certainly use the boron aluminum tubes in support of the fuse large frame, in addition to the decreasing the mass of the space shuttle by more than the 145 kgs. So likewise, if we'll talk about the military applications, these metal matrix composites such as silicon carbide alumina composites satisfy this requirement because they have the high microalloy strength. In addition, the volume fraction of the silicon carbide can be varied to have the coefficient of the thermal expansions compatible with other parts of the system assemblies. If we talk about the transportation is concerned, so metal matrix composites are finding use now in automotive in engines that are lighter than their their metal counterparts, and so on. Automobile applications, marine applications, electrical and electronics applications, sports applications, space applications. So these are some of the examples where we can say that these composite materials are having the applications. Now, some of the research work has been carried out by our research scholars. I would like to share some of the slides over here. See, this is the experimental setups. Arvind might be aware of this. I think their work only. And then we have these facilities where the materials are prepared, and they have done the hardness testing and then the turning operations. At the we have the facility. They have used this lab, and then so they have used the design of experiments, and they perform the experiments, and then they have gone for the machining operations. So during the machinings, they will observe that, see, if we go for the machining of these ductile materials, and if you go for the brittle materials, and if you go for the composite materials, you will find the different orientation of the chips which will comes out. So just some of the examples I would like to share over here. The chips formed continuous but irregular shapes. So so these are the different spindle speeds, fit rates they have taken, and then they have the further observations. So if they have used these composite materials, the chips will be the discontinuous type. And here this is the case of aluminum silicon carbide cases, and this is for the aluminum titanium carbides, and so on. And what will happen overall, that once you will use this machining of those materials, this aluminum beryllium materials, you will find that tool blunt will be taking place, or the tool life will be reduced. So here we have my friends has shown this is once they have machined this composite by having the 1.5% only silicon carbide, and this is the pure alloys, and here we have the 1.5% titanium carbide. So we have observed that in these cases the tool life will be better, means we can have this edges is less distorted. And then the effect of these spindle speeds at a different feed rate on surface roughness. So they have observed, and these are the graphical representations about the surface roughness and the spindle speeds, and is their observations. So if you see those surfaces in the we have in our lab as a 3D profiler meters. So there you can see this the 3D profile of the machined surfaces. If you see that it will appears as a very nice appearance of the surface, but if you see in the 3D profile of meters, the surface will be like this. So these are the some of the case studies of the different composite materials. It is case of the 1.5 silicon carbide composites. In the case of this is the titanium carbide composites and their observations. And further they have studied the mechanical properties, then XRT analysis they have done. The another is they have done for the this optimizations techniques. So before optimization they have gone for the T on, T off, and so on. And this is their outlines of the how they have started their works, and this is the outline of their projects. And then experimental procedure, what they have done it. So this is another scholar who has done those experiments in our labs. And then the tribological, I think this tribological properties, Arvind, it is your side, since na?
Yes, sir. Yes.
Yeah. So this is the tribological test they have performed, and they have observed that this material have the better tribological properties. And then the die sinking EDM, another students they have used this. So, and they have studied the microstructures studies of those aluminum-based metal matrix composites, and they have observed the distributions of the main factor is the in the structures. If the distribution of the particles, if you maintain it properly, you will get the better strength. If the distribution of those particles are not good, see in the case of Arvind only, this is the B4C particles. So the distribution supports it's okay, but further if the much more distributions will be there, if the titanium carbide particles or the boron carbides or the some this other nitrides, then your strength will be improved obviously. So as you know that as per the Hall Potts equations, this as and when the grain size will be the smaller, the strength will be the better. So it's have this having the correlation of the microstructures with the mechanical properties. So this is their observations from the TEM and ACM analysis they have done it, and then they have measured the density as well as the hardness, tensile strength. So and they have noticed about the surface. So when they have done the machining of the surfaces, they observe the how this crack or these particles are 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 flowing from these surfaces. So sometimes it depends so that it's having the very hardness, and it will impact on the tip, and it will damage the tips of or you can make the blends this is tool will become the blunt, or the sharpness will be reduces. So these are the process. And then here wear test they have and they have used the electro discharge machining also, and they have observed the analysis. So by this way they have done some analysis, and these are their conclusions. So these slides I will share you all, and you can have this uh, so if we talk about this, what is their observations that wear rate of this aluminum 7050 B4C composites decreases with the addition of B4C in the matrix, and the mean wear rate eliminates the for the 5%, 7.5%, 10%, 12.5% composites are. So these are their observations and their results. So we can go through that, and then Further, their observation is about the ADM analysis. The ADM machining, such as material removal rate, increases with the increase of percentage of the boron chloride and this current, and then material removal, this tion, and the material removal rate also increases with the increase of surface finish, and then other properties like this is the size of the 200 microns and all. So please, this is I am concluding here itself, Arvind, because I have the meetings and I have to leave for the meetings. And if the time will permits, on the last day, if time will permits, I will take the one special classes for 1 hour if you have any schedule for this.
Sir, thank you, sir. Actually, sir is having a CNET meeting at NIT Agartala at 11:30. So, one request is there, sir. A few of our participants are from electronics and electrical engineering also, and computer science also. So, these materials, what we have discussed right now, how they can be beneficial and how they can think of researching on these materials so that for electrical and electronics it will be beneficial, sir. Right from the composite, can they use, or and if they can use, mean how they can use it, sir? Hello. Sir, you are audible. Sir, you are audible, sir. Now you are audible, sir. Sir, now you are audible, sir. Hello.
आपका नेट चला गया सर।
Yeah, sorry for that. This similar work I have done in PhD. As sir was discussing, there was a technical issues from sir's end. There is a net error at NIT Agartala. Anyway, this similar work I'll continue with. I was fortunate enough to work under him, and my what I have done in my PhD. I'll just give an outline here. So basically, I have developed one composite material that was based on the aluminum alloy 7050 series and B mixing a B4C Ex-situ composite. So this there's a basic difference between Ex-situ and in-situ. In-situ we'll have a alloying kind of thing. We'll melt it and do inside that melt. And Ex-situ means we are additionally we are adding from outside and trying to make a bond with the matrix material and then so this is the Ex-situ method, and that was developed through a stair casting method. So after developing a composite, we have gone through a heat treatment as per the specification of T6, which was prescribed for aluminum alloy 7050. And after that, once we have got the material mechanical testing to travel composite. So yeah, not going much into it. One second. So basically, this contents was like this. Which were like this. As in every PhD work, it happens right from introduction, literature review, motivation and objective, experimental procedure, result and discussion, conclusion, future scope. So here the motivation was very clear to develop one composite. These are the literature review. Will not have. Motivation was very clear to develop a composite material. Aluminium alloy B4C based composite material, and that was this material have a good affinity since B4C has good affinity towards the aluminium. So I have chosen this reinforcement ceramic particle B4C, and the size, if I remember that that was 100 micron size B4C particles were there, which I have used here. So an objective was also clear to develop a composite. I have gone up to 12.5% of B4C. Then through the flux assisted stair casting, we have gone for heat treatment. Then several mechanical testing we have gone. And basically for the bond formation mechanism, we have tested through several XRD. Then we have gone for FESEM, and we have established a quaternary layer of B4C TiB2 L3Ti aluminum titanate and aluminum particle matrix interface, and the microstructure. So the corresponding microstructure. I have published one paper also in this, and that was highly recognized. So then we have gone for several kind of mechanical testings, right from density, then hardness, tensile, compressive, and impact test. After that, we have tested the tribological property of that developed composite material, and of course that was ornamental by this optimization method, and there also it has proved that the method what we have selected was good. And then at last, we have also done the machinability property of the developed composite. And these were the output what we have done through electro discharge machining. So basically, this was the experimental setup which I have used. I have used aluminum alloy 7050. Here, the major alloying element is zinc, that is 5.88. Other things, well, I did. And boron carbide I have used, that is, and size was 100 to 150 micrometer. The flux assisted, since I have mentioned that, so I have used flux assisted stair casting method. So flux was this K2Ti6, that is potassium hexafluorotitanate, and then one degasser I have used, that is hexachloroethane. So amalgamating everything together, and say this is the iron mold I have used. Uh, this is the stair casting method, which was there that NIT Agartala. Then I have tried that from 7 to 800 degrees centigrade. We should not pour it directly at room temperature. So that heating chamber was developed so that their temperature was fixed at 450 to 500. So this was moreover 400 to 450 degrees centigrade. And then we have poured it into it, and we have gone for a slow cooling so that mm, shrinkage alliance to reduce the shrinkage alliance. Then for heat treatment, I have used this setup. So these were the test samples were made, and density were checked accordingly. This was the tribological setup which Sir has also shown. These are the small components, small size. The size was fixed at 30 diameter, and um, 30 in size, and 6 diameter. Sorry, 6 diameter and 30 in length. That travel pin have used, and I have put it in this two wear pin, and then we have rotated against a steel disc EM34 24 discs. EM31 disc have used. Against that, it was rotated, and we have seen the wear property of this. And this die sinking method I have used. So these were the properties, these were the parameters which I have selected. And they say this is the composite, and here is the copper pin I have used as a tool. And of course, the hardness of this one is very hardness of our composite was very high compared to this copper. And since I have used electro discharge machining, so setup is as like this. And so the major finding of this composite was here, right from 0%, 5%, 7.5%, 10%, and 12.5%. I have seen that as I have increased the number of percentage of reinforcement, we have a uniform distribution of this one. So this distribution, what is had done, it has shared the load which was coming on the composite, and hence the load bearing capacity increases here. As the since the major challenge of the this kind of casting is the distribution of particle. If it is distributed, then it will show a good property. If it is not, then of course this will be having a bad properties on the composite. Motive was to develop a reaction layer. Actually, B4C composite, B4C particle, when it comes in contact with the aluminum matrix with the systems of flux, there is a locally increase in the temperature. Since the melting temperature of B4C is about something around 22, 2300 degrees centigrade, and this aluminum is 660. So there is a huge difference between the two melting points. And if it is not melted, then we'll have a solid liquid mixture. So we have tried to put some reagent which has locally increased the vicinity temperature of the B4C particle locally at the periphery. And there it has that react with the aluminum matrix, and then it has formed a layer. I mean the layer of this one. Layer means here you have shown one block. This I have tried to show this reaction layer like this. There is a B4C particle at the center, and just vicinity to B4C, there will be a layer of TiB2 or TiB3, like layer will be there, titanium borate. Since titanium is the major reacting element, this titanium increases the local temperature of that B4C particle near that, and have a that reacts, it will melt and then react with the matrix, and it will form TiB2, then Al3Ti, and then alpha aluminum. If this kind of reaction happens, then only we can be sure that our composite has been have formed. So I was able to achieve this kind of reaction with this. This is the one EDS also we have done, and through XRD also several whatever method was there available. I have checked, and this is the interface we have achieved, and with this uh, diagram also we have seen that this is the L3T, L3Ti, TiB2, L3B, LB2, like that. So with this, it was confirmed that the reaction layer was perfect. So next, this was the density and hardness, right? This is tensile property. Actually, what happens when you go for a higher increase of that, there is a chance of porosity with that. So optimum temperature, optimum percentage for mixing B4C into aluminum is up to 10%, or even less than that. Before the beyond that we goes, that property decreases. So similarly, like impact stress also, this has happened. As sir was showing this, wear property has wear performance has increased since before C particle was it was uniformly distributed. So this one. Uniformly distributed. So all the loads which were coming to that matrix was shared by the particle. And since there is a strong bonding, there's a particle also will not coming out from the composite. And similarly, it has shown a good property. So one can the beginners can think of making such kind of composite for shoe pad or automobile shoe or like that, because this is has good thermal conductivity also. So this can be a good material for brake shoe. So, keeping in that view, that one, I have tested the typological property of B4C based aluminum alloy 7050 composite. Since the uh, this fatigue strength of the alloy is high compared to other aluminum series. So, and this if we impart if we mix before C, it will have a good wear property. So all together will have a good property, good material for shoe brake. uh, uh, we have to work on that, and if we keep in this into view, we can make definitely we'll go for this kind of research, so that a new material will be developed. Keeping ahead, so these were the optimization technique. Okay, next, electro discharge machining I have done. Actually, the motive of doing this was, um, as sir was showing one slide, there is a tool blunt or kind of issues. So this happens because this ceramic particle is very hard, and boron carbide is hardest material, second hardest material, even after boron nitrate or diamond. So if these materials are very hard, and if this material will be machined by a kind of tools, HSS or these tools, there will definitely a blunt of tool, and surface finish will be affected. So machining these materials with the conventional machining process is not fruitful. We have to go for some advanced machining processes. So among all, I found that electro discharge machining is good for them, because in electro discharge machining we have this functions based on the spark erosion, erosion of a spark. So this for the short duration, a high current density between the tool and electrode forms. It is EDM is a non-contact type machining process in which material removal takes place by meticulous erosion of workpiece through a series of electric spark of a small, short duration and high current density between the tool electrode and the workpiece. So this, as I have discussed here, there is a small gap between the tool and the workpiece. So this is totally non-contact type. Here the hardness will not impact anything on machining. Only thing is these two materials should be electrically conducting. Okay. So then this narrow gap is submerged in electrically non-conducting dielectric fluid, generally hydrocarbon oil in case of die-sinking EDM, or if you go for wire cut EDM, it is ionized water. So the predominant factor of electro discharge machining are the three factors are there. One is the peak current, what we are using, on time, so how much spark time we are giving, and what is the gap voltage is there between. That gap voltage actually creates a electric field between them. Actually, if it is if it is a non-conducting this one. Uh, Dielectric material, and if the charge has to flow from electrode to workpiece, so this electric gap voltage plays a very important role. It creates, if you put fix a gap voltage, it creates a electric field between these two, as I shown in a figure, as setting a plasma channel, and this plasma channel, here the spark occurs. So if it is depends on us which was is negatively charged and positively charged. So negative ions comes through the positively charged. Again, here is the question: which one we have to make positive, which one we have to make negative. Generally, we go for a tool as a negatively charged, and workpiece as a positively, because the two regions are there. The reason is electrically discharged material having less weight compared to the positively charged. One thing. Uh, then, so this is the reason we use workpiece as a positively charged, because we have to remove the material from the workpiece. So more material will be workpiece, will be removed from the workpiece if you put tool as a negatively charged. Again, here in this process, both the materials, tool and workpiece, get eroded, and compared to tool, workpiece erosion is a more here. So here, this is when negatively charged ion, there's some huge amount of temperature increases, and this was ranges up to here 22,000 degrees centigrade, and heat flux of 10 to the power 17 watt per meter square for very short duration of time, and subsequently both electrode and electrodes, means workpiece and tool, will get melted and evaporated. So this is the beauty of this electro discharge machine, that here the hardness of the tool or material will not affect the machining process. So this is the keeping this as a plan of experiment. I have since I have developed 5 composites and 5 type of composite. So there was a 5 type of materials, and I have gone through hole I have made to the workpiece, as I have seen here their plan. Here, since this is there is a hole has to be made with this tool here. So consequently, this was the parameter I have used. That is the percentage of B4C as one. Since I have developed 5 composites, so 5 parameter. One parameter is also this percentage of B4C. Then pulse current was there, pulse on time, the spark gap, and duty cycle was the 5 parameters I have process parameter I have chosen. Then the machining process, the sinking medium on this composite, and responses what I have um, found is this material removal rate, tool wear rate, then drilling speed. Since this is also very important, drilling speed, surface roughness, radial overcut, radial uh, top overcut and bottom overcut. So there will be a slant or taper kind of thing with this electro discharge machining. So these are the factors which we have to consider for while doing machining on the composite material. Then circularity was another concern. Is another concern, because since in any machining of composite material, the circularity is a major issue, cylindricity and taper angle. So these were the response, 9 responses I have found with this composite, and this was a good also. Okay, yeah. So here I have seen these are the responses being used here, and so it's see this is the, I mean, the microstructure which we have after that machining. What happens at the surface of the, so resolidified metal? Actually, what happens? Uh, there was a crater development uh, as this current increases. That there was a bunch of material will get evaporated and melted. So there will be a local surface roughness increases here. But these are the factors. Is a spherical deposits. So, suppose solidified this one. mm, mm, Debris will be deposited on the surface, and that can be there. So this can be done simply by a sand blasting or something. So a smooth surface you will get, and this is on the micron level. Generally it is very smooth surface we are getting with this, and these are the observations which we have gone through this. And so this is the conclusion that we have successfully mm, prepared a composite through flux-assisted casting method, and synthesized it. And this composite was gone through this heat treatment process. Then we will be able to make a uniform distribution of matrix with a proper incorporation by forming B4C, TiB2, Al3Ti and aluminum. That is a quaternary layer. If we form then we can have a good composite, load-bearing composite here. And with the consequence of that, we have got a very good mechanical properties also as well. So this reaction, so this encapsulating layer prevents the decomposition of B4 particle in this. Actually, what happens if this layer is not developed? What will happen? This B4C or other particle will get decomposed and make a sort of uh, brittle particles inside the microstructure and reduce the its strength. So this layer actually encapsulate the B4C particle, mixing with the making a proper bond with the matrix, and this decomposition decreases. And if this brittle phase, it will make a brittle phase if it decomposes and reduce the property of the matrix. We will not get a desired property as we are planning to thinking to get. So then tensile strength increases. Obviously, then UTS as like this. Some all the properties has increased. Wear rate has wear rate the composite decreases by the addition of B4C. Means the composite having B4C mixed having less wear rate. It is less wear. So obviously that can be, as I said, that can be that can be a material for breakthrough or something. We have to think like that and we have to work like that. This material is equally good to make breakthrough, especially for railways. So we have gone to that, and then uh, for machinability check, we have this kind of uh, um, findings. We have found that 9 responses I have found, and there was by optimization the error between that was 2.81, which is well within the acceptable threshold. So that was this one. Future scope is very clear in this work that secondary manufacturing process like forging, rolling can be done on this, so that secondary manufacturing means after making that ones, we have to go for forging or rolling of the composite. If that particle is not breaking inside that, so that we have to take care. If you go and press it, there will be a chance to break it, because if you go for hard forging, there will be a chance to break that particle into it. So that broken particle will reduce that property. So we have to take care of this one. But again, secondary manufacturing will also always give a good impact. So keeping all those pros and cons, and we'll have to be careful while making. So one thing is secondary manufacturing, like forging, rolling, can be done on this composite, and its effect on microstructure, mechanical property, typological properties, as well as machinability may further be studied. So this is one area for the beginners. I am giving you the gap of your research, so you can continue on this, and you can um, do your work on this composite itself if you go for uh, secondary for the manufacturing process. Weldability studies I have not done, so this is another area is there. You can work on the weldability of that aluminum B4C composite, uh, which may improve the application of this in industry. Also, weldability study on a rolled and forged composite can be carried out. Obviously, weldability is another issue, which welding is also very important. So, on weldability as a whole, we can study on this. So these were the references I have used. Some of the publications which I have made during my study, PhD, 4 SCI, 5 scopus, and then conference papers. So all was done this So new beginners can continue with this research. And so I will share Sir's PPT to you all on that WhatsApp group. So everyone is requested to join the group, check your mails regularly. We will be updating you everything on that mail. Uh, on WhatsApp group, we will be updating you. So we'll update you every further updates on this. And tomorrow session we will start at 10 o'clock. Sharp at 10 o'clock. There's a Professor G. Krishnaiah. He is a professor at Triple IT Kurnool, which is in Telangana state, near to Tirupati. So he has done his PhD from IIT Kharagpur, and then he has worked abroad also. So he has good hands-on experience on working with robotics and all. So tomorrow's topic will be on robotics. So I'll request you all to I'll share, or the same link will be there to, or if any updates we will share on the WhatsApp group. So everyone requested to join the group which we have created. Mm, Updates will begin, and keep on checking your mails. We will update you all things on that mail and WhatsApp group. Okay, so today's session, HOD sir, anyone has any question, please you can put your question. You can type your question if you have any doubt, any query, any improvement you want. Uh, Please type your questions. So I hope this session was beneficial to you. Dr. Rai is sir is always available for everyone. He is very kind-hearted person. So if any uh, uh, query you have, you can send mail to me also, or you can send directly to him. I will share his email ID to you all. So sir will definitely help you. So I hope this session was very beneficial to all. We'll continue the session from to tomorrow at 10 a.m. So everyone requested to kindly log in on time. Thank you. Thank you very much.
Thank you, sir.